Okay, last time we looked at the n equals 0 case for the error in a Taylor polynomial. This time we're going to step it up a notch and look at n equals 1. Alright, so we need to see what we can say about the absolute value of t sub 1 of x minus f of x. Now, just like the n equals 0 case, f might wiggle around in some crazy way that we have no idea of knowing about. So without adding a condition, we have no idea of what this error might be. So just like before, we're going to insist that the derivative of f not get too large, but this time we're actually going to go to the second derivative. So we need to assume that the second derivative of f is never bigger than some number, m. Okay, with that in mind, let's see what we can do. So also just like before, we're going to start out by getting the base point in here. So this is exactly the first step as in the last video. We can write t sub 1 at the base point minus f at the base point. And that's because this stuff in the parentheses is really just 0 because the first Taylor polynomial and f agree at the base point. Okay, next, I keep changing my brush size. Next, just like in the n equals 0 case, we can use the fundamental theorem of calculus to write this as an integral, so absolute value of the integral from a to x of the derivative with respect to t of t sub 1 of little t minus f of little t dt. Okay, and then as in the previous case, we can compute this derivative inside here. So absolute value of the integral from a to x of t1 prime at little t minus f prime at little t dt. And again, just like in the previous case, we can move the absolute value inside the integral if we put an inequality right here. So less than or equal to the integral from a to x of the absolute value of t sub 1 prime at little t minus f prime at little t dt. And now something interesting has happened. If you look right here, this integrand, this is the error in the 0th Taylor polynomial for f prime. Now this is using the last preliminary fact from the first video. This part here, the first derivative of t1, this is the 0th derivative. The 0th Taylor polynomial for f prime. So what we have in this absolute value is the error in the 0th Taylor polynomial for f prime. But from the last video, we have some idea of what the error in the 0th Taylor polynomial is. So integral from a to x of our error bound from the last video says that this absolute value inside is definitely no bigger than capital M times the place where you're evaluating the function, which is t, minus the base point, and the base point is a. All right, so now we can compute this integral. And this integral is very doable because it's a polynomial. I move the m outside, integrate the stuff inside the parentheses with respect to t, you get 1/2 t squared minus a times t. Evaluate this at a and at x. And you get, you know what, let me do this a different way. Back up a little bit. So this integral is not the integral. This is m times t minus a from a to x. Yes, that's what I want. Oh, I need a squared right here, and I need an over 2 right there. This might not be the your first choice for how to write down the antiderivative here, but if you check it, it does work. If you take the derivative of this thing, the 2 comes down, cancels the half, the power changes to a 1, and the chain rule for t minus a just spits out a 1. So it does work. And then when you plug in a, you get 0, so let's just plug in x. You get m over 2 times the absolute value of x minus a squared. And up here, these should have been absolute values to begin with, actually. Okay. So finally, we have an error bound for the order 1 Taylor polynomial. Well, you might be starting to see a pattern form here. We have some magic number m. We have a power on x minus a that matches the denominator here. If you keep doing this, you'll see actually there's a factorial here. So there is a pattern forming, and if you very carefully do a proof by induction, you can prove that the pattern holds. So here is the pattern in general. So choose your order n and your base point a. And assume, additionally, that the n plus first derivative of f is bounded by some number m between a and x. Okay. And in this case, the difference between the nth Taylor polynomial and the original function is definitely no larger than our magic number m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. All right, so we have some kind of bound for how far apart the Taylor polynomial and the function can get. It is a little hard to see how to use this error approximation because, well, if nothing else, because of that m. It's hard to see exactly what m is saying. So what we're going to do next is look at a couple examples of actually calculating this error bound so we can see what it actually tells us. So off to part 4.